Hey, good people, Arthur Morris here. I hope all is well. In this video, we are going to look at integration by substitution. So the anti-differentiation of a composite function says to let g be a function whose range is an interval I, and let f be a function that is continuous on that interval of I. If g is differentiable on its domain, capital F is an antiderivative of lowercase f on the interval I, then we have the following. The integration of f of g of x times g prime of x dx is equal to the antiderivative of g of x plus c. So by letting u equal g of x, it gives us a du of g prime of dx. And then we can integrate the function f of u du to find the antiderivative. So basically what we try to do if we have a composite function like this, we look for one of the two functions that's the most complex, and we let that function be u, and finding du hopefully gives us g prime of x. So hopefully it will give us the rest of the function, the other part of the function. And then we can integrate f of u du, which makes the problems a lot simpler. So the general power rule for integration, if g is a differentiable function of x, then we have the power rule here. So we have the same thing for u. If we're integrating u to the n power of du, then u to the n plus 1 over n plus 1 plus c, where n is can't be equal to -1. So we use the power rule here with these type problems. All right, my friend. Let's look at this a few problems. So this particular problem, number 5, we're going to integrate 1 plus 6x to the fourth times 6. Now the alternative here is to multiply 1 plus 6x times itself 4 times, and then multiply that times 6 and then integrate. Or if we look here at this inside, and most of the time again when you use UDU substitution, you let u equal the most complex part of the fraction, which more than likely is going to have an exponent outside of it. So let's let u equal, I'm going to let u equal 1 plus 6x, and our hope is that du, or some form of du, will be equal to the other part of this function here. So the derivative of 1 plus 6x is 6 dx, which is that other part of the function. So now we have that as u, and we have that part as du. So that allows me to rewrite this as the integration of u, still to the fourth power, times du. So I just wrote it in terms of u instead of x here by using substitution. So I'll replace 1 plus 6x with u because I said that's 1 plus 6x. The derivative of u is 6 dx, so I'll replace 6 dx with du. So now let's integrate this, because now this is a lot easier to integrate using our power rule. So that would be u to the fifth all over 5 plus c. And then last but not least, we want to rewrite this back in terms of x. So now we want to replace u with what it was equal to, which is 1 plus 6x. So 1 plus 6x to the fifth power all over 5 plus c. So the integration of that original problem is 1 plus 6x to the fifth power all over 5 plus c, or you can write that as 1/5 times 1 plus 6x to the fifth power. Okay, so let's look at number 6 here. So again, we have x squared minus 9 raised to the third power times 2x dx. If you look inside of here and look at the derivative of x squared minus 9, we see that it's 2x dx, which is the other part of this. So let's let u equal x squared minus 9. Then the derivative of u is equal to 2x dx. All right, so again, this part is u, that part we found to be du. So I can rewrite this integration in terms of u. So u to the third power du, just using substitution there. Now I can use my power rule, so add 1 to the exponent, so u to the fourth, and again you can divide it by 4 or multiply it by 1/4, however you want to write that, it's fine, plus c. Okay, so now that we've integrated that, I want to go back and write this in terms of x by substituting back in for u. So that's equal to 1/4 of x squared minus 9 to the fourth power plus c. Okay. What about number 7 here? We have the integration of the square root of 25 minus x squared times negative 2x dx. So the first thing I want to do is to write this in exponential notation. So I'm going to write this as 25 minus x squared to the 1/2 power. And then again, here again, you want to look at the most complex part, which again, if you see this 25 minus x squared all raised to the 1/2, and let that u equal to 25 minus x squared. That's the hope. And if we look at the derivative of that, that's negative 2x dx. So that works out. So we will let u equal 25 minus x squared. And the derivative of that would be negative 2x dx. All right. So now we can use u du substitution. Replace 25 minus x squared with u. Replace negative 2x dx with du. So we want to integrate u to the 1/2 power du. All right, so we add 1 and divide. So if we add 1, that's adding 2 over 2, which is 3 over 2. If we divide by 3 over 2, that's the same thing as multiplying by 2/3. Okay, so 2/3 times u to the 3/2 power plus c. And then rewrite this back in terms of x. So replace u with what we let it be equal to up here, 25 minus x squared. Simple as that. All right. Let's look at another one. All right, all right, all right. Let's see what we have here. On number 11, we have, for number 11, we have the integral of x squared times x to the third minus 1 x to the fourth, or to the fourth power dx. So the first thing I would like to do is to move this x squared by the dx. So we have x to the third minus 1 to the fourth power times x squared dx, since we're using the u du substitution. And now we want to let u equal the most complicated part, complex part, which is the x to the third minus 1. And we're looking for du, or some form of du, to equal x squared dx. All right, so right now du equals 3x squared dx. All right, so that's not quite x squared dx, but I can divide both sides by 3 here in my derivative, or multiply by 1/3, and that tells me that 1/3 of du equals x squared dx. And that's what we wanted. We wanted that x squared dx. Excuse me. Okay, so what we have, we want to replace the x to the third minus 1, that's equal to u, and the x squared dx, and this time is equal to 1/3 of du. So we have the integral of u to the fourth times 1/3 of du, because 1/3 of du equals x squared dx. Okay, so let's bring that constant out front, the constant multiple out in front of our integral. So we have 1/3. Now we add 1 and divide, so that'll be u to the fifth divided by 5. So dividing by 5 is the same thing as multiplying by 1/5. Okay, so we end up with 1/15 u to the fifth plus c. And remember, our goal is to write this in terms of x, have this in terms of x. And if you look back up top, we have it, we let u equal x to the third minus 1. So our final step would be to replace u and write this back in terms of x, the x to the third minus 1. So 1/15 times x to the third minus 1 raised to the fifth power plus c. Okay, let's look at another problem here. Let's look at number 15. All right, so number 15, we have 5x times the cube root of 1 minus x squared dx. So again, I'm going to rewrite this with cube root. Let's see here. If we look on the inside, that's negative 2x. Let's go ahead and bring this 5 out, this constant multiple out as well. So let's bring that 5 out in front, because we don't, having that constant multiple there won't help us, because if we look at the derivative, that will be negative 2x on the inside. So let's say 5. And then let's write this in fraction notation, 1 minus x squared raised to the 1/3. And then take this x and move it by the dx. Okay. So I brought the constant multiple out front, and I rewrote the radical in fraction notation, and then moved the x by the dx. Okay. Let's see here now. Let's let u equal 1 minus x squared. And this time we need our du to equal x dx, or some form of du. So right now du equals negative 2x dx, but we want it to equal 1 dx. So we want to divide both sides by negative 2. Just the same thing as negative 1/2 of du equals x dx. So we know negative 1/2 of du equals x dx, and we know that u is equal to 1 minus x squared. And this is the function that we're working with, so we have to keep in mind that we have that 5 constant multiple outside of that integration. All right, so let's rewrite this, keeping the 5 outside of the integration symbol, times the integral of, we're replacing 1 minus x squared with u, so u to the 1/3 power. And then we are replacing x dx with negative 1/2 of du. Okay, so same thing as last time. We want to pull that constant multiple, the other constant multiple out in front. So we have negative 1/2 times 5, or 5 times negative 1/2 now, times the integral of u to the 1/3 du. Okay, let's use our power rule to integrate. So we have negative 5/2 times, I need to add 1, which is the same thing as adding 3 over 3, which will be 4/3. So we're dividing by 4/3, or multiplying by 3/4. So we have negative 5/2 times 3/4 times u to the 4/3 plus c after we integrate. Okay, so let's clean this up and replace u, write this back in terms of x. So now we have negative 15/8 times, and u was equal to 1 minus x squared. So 1 minus x squared raised to the 4/3 plus c. All right, let's keep going and look at some more examples. All right, so this one we have the integral of x over 1 minus x squared dx. Okay, so the process is the same, so let's just run through it. We have 1 minus x squared, which we can rewrite that and move it up top. So as the integral of, and remember that would be to the 1/2 power, so when I move it up top, that makes it the negative 1/2 power. Okay, so let's let u equal 1 minus x squared. So if u equals 1 minus x squared, keeping in mind that we want some form of du to equal x dx. So if u equals 1 minus x squared, then du equals negative 2x dx. But we only want x dx, so we need to divide both sides by negative 2. So negative 1/2 of du equals x dx. Okay, so now I can rewrite this in terms of u, replacing the 1 minus x squared and the x dx. So that's u to the negative 1/2. And then x dx, and this time is equal to negative 1/2 of du. Okay, so keep going through the process, bring the negative 1/2 back out in front. And then integrate, so we need to add 1, which is the same thing as adding 2 over 2. So that gives us positive 1/2. And if we divide by 1/2, that's the same thing as multiplying by 2. Okay, so we added 1, or we added 2 over 2, which gave us positive 1/2, and then we had to divide by 1/2 for our integration, which is the same thing as multiplying by 2. So negative 1/2 of 2 is negative 1. So we have negative u to the 1/2 plus c. All right, and u is equal to 1 minus x squared. Okay, now let's look at some definite integrals using this same information, substitution, same process. Let's look at a couple of definite integrals. So we're going to use the same process, but then we want to find the actual value with the given upper and lower bounds here. Okay. So you guessed it, I'm rewriting this. to move the x over by the dx. And you don't have to do that. I just like to do it. Okay, so look at this and you need to think about what would you let u equal. For me, I'm going to let u equal x squared plus 1, and I know my du, or some form of du, needs to equal x dx. X squared plus 1, and then du equals 2x dx. I need it to equal 1x dx, so I'm going to divide both sides by 2, or multiply by 1/2. So 1/2 of du equals 1x dx. So now I can write this integral in terms of u. Keeping in mind that x dx is equal to 1/2 of du. Right, bring the 1/2 out front and integrate. So I'm going to add 1 and divide by, or let's see here, we'll go step by step. Now integrate using the power rule. So we want to add 1, which will give us 4, divide by 4. It's the same thing as multiplying by 1/4. And instead of plus c, we have a definite integral here, so we know we're going from -1 to 1. So let's go ahead and write this back in terms of x. So we have 1/8. And then u is equal to x squared plus 1. All right, and then from here is substitution. So remember, it's the upper bound minus the lower bound. Okay. So we have 1 squared plus 1 divided by 8. And this should be to the 4th power. So 1 squared plus 1 to the 4th power divided by 8. Same thing as multiplying by 1/8. Minus -1 squared plus 1 raised to the 4th power divided by 8. So 1 plus 1 is 2. 2 to the 4th is 16. 16 divided by 8 is 2. Same thing here. 1 plus 1 is 2. 2 to the 4th is 16. 16 divided by 8 is 2. So the definite integral of that function is from -1 to 1 is 0. So the area underneath the curve equals 0. Okay, and let's look at one more. Let's look at number 59. Okay, and you may want to pause it and try this problem for yourself. Okay, so I see that we have 2x plus 1 raised to the 1/2 power, 1 over that. So I'm going to move that 2x plus 1 to the 1/2 to my numerator. Okay, and same thing, because I have that exponent out here, let's try u du substitution. So let's let u equal 2x plus 1 and du equals 2 dx. I want my du to equal just 1 dx, which is the other part of that. So I need to divide both sides by u, or multiply by 1/2. So 1/2 of du equals 1 dx. So now I can substitute. So I'm going from 0 to 4, and I have u to the -1/2 power, and then du is equal to 1/2 of dx is equal to 1/2 of du. Okay, so let's bring the 1/2 out front. And let's integrate. So u to the negative 1/2, integrating that means I need to add 1 to that exponent, or add 2 over 2, which makes that u to the positive 1/2. And if we divide by 1/2, that's the same thing as multiplying by 2. So I have 1/2, and then I have times 2, and u to the 1/2, integrating from 0 to 4. Okay, so 1/2 times 2 is simply 1. Let's rewrite the u in terms of x, and that's 2x plus 1. And remember, 1/2 is the same thing as the square root. So we have the square root, and let's take it step by step. So u, let's see here. So 2x plus 1 raised to the 1/2 from 0 to 4. And then we can write that back in radical notation. 2x, the square root of 2x plus 1 from 0 to 4. And then integrate the upper bound minus the lower bound. So the square root of 2 times 4 plus 1 minus the square root of 2 times 0 plus 1. So 2 times 4 is 8, plus 1 is 9. The square root of 9 is 3, and 2 times 0 is 0, plus 1. Square root of 1 is 1. So integral equals, the definite integrals equals 2. Alrighty, my friend, I hope you found this video to be helpful, and I will see you on the next one. Thank you.